Hi, it's Mr. Anderson, and this is AP Physics Essentials video 49. It's on momentum, which is just the product of the mass of an object times its velocity. In 1895, a train was headed towards Paris. They were a little bit behind schedule, didn't apply the brakes in time, and it came shooting out through the train station. What was their problem? They had too much momentum. And if you were to ask somebody what is momentum, they'll probably come up with a pretty good definition that would fit in physics. Momentum is always going to occur if we have an object that's in motion. And if you want to calculate it, you simply multiply the mass of the object times the velocity of the object. The greater the mass, the greater the velocity, the greater the momentum is going to be. And so if we want to change our momentum, what could we do? Well, we could decrease the mass, we could increase the mass, or we could change the velocity. What's the easiest way to change the velocity is to apply a net force to that object. If we apply a net force to the right to this object, what are we going to see? We're going to see an increase in momentum towards the right. Let's say the object is moving towards the right and we change the net force on the object. What's going to happen? It doesn't happen instantaneously, but what we'll see is a change in momentum that reflects that net force. And so if we define momentum, the equation is P equals mv, where we're multiplying the mass of an object times the velocity of the object. So if we have this cart here, a 1.0 kilogram cart, and it's moving with a velocity of 2.0 meters per second, figuring out its momentum is really easy. You simply multiply 1.0 times 2.0, and so our momentum is going to be 2.0 kilogram meters per second. And so if we add velocity to the right, we're going to increase that momentum. Now, one thing that you need to remember is that the net force on an object is going to affect that change in P, or that change in momentum. And so let's say we have an object like this, a cart that's at rest. It has no momentum, but we apply a net force to it. How would we do that in a physics lab? We're just going to connect it to a weight. And so now we're going to apply a net force to the right. What's going to happen to our momentum? It's going to increase to the right. What happens if we increase that net force? If we double the net force on the object, what's going to happen? We're going to increase the momentum more quickly. Let's say we triple it, we're going to see an increase in momentum to the right. And so it's a direct relationship between the net force on an object and the momentum on that object. But let's make it a little bit trickier. Let's say that object is moving now towards the left, but we're applying a net force to the right. What's going to happen? Well, eventually what's going to happen, let's watch, is it's going to slow down and then it's going to start to accelerate to the right. And so even though it was moving to the left, as we apply a net force to it, eventually that momentum is going to move in the direction of the net force. Now these are pretty easy problems because we're just looking at one dimension. But when you were growing up, like me, you probably played video games like this. And so if I turn the ship and move it in this direction and blow up an asteroid, it's all momentum. But I would find myself playing asteroids like this. I'd be moving in one direction, but I'd be applying a force in another direction. In other words, my momentum is in that direction, but my net force is in a totally different direction. What's going to happen to that? Well, it doesn't happen instantaneously, but what's going to happen is that ship is eventually going to move in the direction of the net force. And so did you learn to justify the data we need to collect to show that the net force eventually impacts the change in momentum? I hope so, and I hope this was helpful.